So today we're theorems in all. You have the printout of the worksheet. You can follow along with the notes. But we're going to talk about the Exterior Angle Inequality Theorem, and then there are 6 theorems that we're going to use to prove lines are parallel. And try not to get freaked out at the number of theorems, because the 6 theorems for the parallel lines are very similar to each other. But let's first talk about the Exterior Angle Inequality Theorem. And an exterior angle is defined as the supplement of an interior angle. So there are essentially 6 of them. So for instance, angles 4 and 5 are exterior angles because they are supplementary to 3. There would be another 2 exterior angles, let's say 6 and 7, because they are each supplementary to angle 2. And then there'd be another 2 exterior angles over here, we'll say 8 and 9, because each of those are supplementary to angle 1. So that's basically what an exterior angle is. So it's outside the triangle and supplementary to one of the interior angles. Now we define or kind of distinguish the interior angles into 2 kinds. There's the adjacent interior angle, which just means next to. Right, adjacent meaning next to. And then the remote interior angles, remote kind of meaning far away, if you want to think about that. So we can kind of say that remote means far away, whereas adjacent means next to. So if we are looking at angle 4, then angle 3 would be the adjacent interior angle, and 1 and 2 would be the remote interiors, and the same for angle 5. As another example, if we're looking at angle 6 as the exterior angle, 2 would be adjacent, angles 1 and 3 would be the remote interiors. And essentially what the exterior angle inequality theorem says, and when we're using this, our little abbreviation for the exterior angle inequality theorem will be exterior angle inequality theorem. And it just says that the exterior angle is greater than the measure of either of its remote interiors. So angle 4 is greater than angle 1. Angle 4 is also greater than angle 2. And the same for angle 5. So that's basically what the exterior angle inequality theorem says. And what we're going to do on the next slide is we're going to prove this. Now this is a proof that we would not expect you to be able to come up with on your own, because there's a lot of clever little things going on in this proof. We're going to kind of write it down informally, so I'm not really going to set up a chart and table and statements and reasons, all that kind of stuff. But the idea here is we're going to use the midpoint of BC because we know it exists. And actually, let me switch to a red for this. So we have this midpoint, and we're going to call it M. So M is the midpoint of BC, so we know that this is congruent to that, because we know M exists. What I'm going to do is I'm going to draw a segment from A through M, and I'm going to make it a length such that this part here, AM, is the same length as M, and we'll call that P. Okay, because we know at some point along line AP, there's a point where AM and MP will be the same. So we can say, hey, we're going to stop at that point. So those are congruent. And all we're really going to do is we're going to connect C and P. So now we've made 2 triangles. All right, so we know AM is congruent to MP. And that's essentially given. I mean, we drew it in there so that it was. We know that BM is congruent to MC. And that's by the definition of midpoint. And then we know that angle AMB is congruent to angle PMC because they are vertical angles. Just realized that it didn't connect. Okay. So that makes those two triangles congruent. So we can say that triangle BMA is congruent to triangle CMP. And that's by SAS. So what that means is that this little angle 1 right here that we're adding is congruent to angle B by CPCTC. Now, angle B is a remote interior angle to angle BCD. So if we're looking at angle BCD from the original picture, and maybe it would help if I redrew that. So A, C, D, B. So this angle right here is the exterior angle, and then this one is the remote interior. So what we're trying to prove is that angle BCD is bigger than angle B. Well, the idea here is that angle 1 from the picture above, so if we kind of draw this in, here's angle 1. Since angle 1 is a piece of angle BCD, and angle 1 and angle B are congruent, angle BCD has to be greater than angle B. So essentially what we're saying is that angle BCD is greater than the measure of angle 1. Right? And we can just say something like, because angle 1 is a part of angle BCD. And then since angle B and angle 1 are the same, then we can substitute and say that angle BCD is greater than angle B. Okay, and that's basically what we were trying to prove, and we used substitution to do that. Now again, this is not a proof that you'd be expected to do on your own, but you should understand where it came from. And what we're doing is we are proving the exterior angle inequality theorem. So now that we've proven it, we can use it as is necessary. And here's where you're going to use it. So here's a few examples if you go to the next page of your notes. We got our friends, the restrictions that you guys loved so much the first time around. So now what we can say is that since x is an exterior angle, we know that it's got to be bigger than 80. And then the only other restriction is that it has to be less than 180, because that's the biggest that it could be. Over here, x is an exterior angle again. So in problem 2, x is an exterior angle. And it's got to be bigger than 27, and it's got to be bigger than 91. So what we can say is that if x is bigger than 91, it's guaranteed to be bigger than 27. So we'll say x is bigger than 91, but less than 180. In problem number 3, x is an interior angle this time. The exterior angle in this picture will be the one that is supplementary to 129. So this is 151. So we know that the 151 as an exterior angle must be bigger than x, which is a remote interior. So we know that 151 has to be bigger than x. And x just has to be bigger than 0. Now problem number 4, there's two triangles. So we want to kind of consider them separately. So if we look at just this triangle on the left, in that left triangle, x is an interior angle. The exterior angle for that triangle is the one supplementary to 24, so that's 156. So we know that x has to be less than 156. And if we just stop there, then we would say that x is greater than 0 but less than 156. However, if I look at this other triangle, we'll say the green one. Okay, so this green triangle here For this one, for this green triangle, x is an exterior angle. As an exterior angle, it's got to be greater than the remote interior, which is this guy right here. So what we're saying is that since x has to be bigger than the remote interior, it's got to be bigger than 80. So we're able to say 80 less than x less than 156. And that's all our work that we're going to do today with the exterior angle inequality theorem. So now we're going to move on to proving that lines are parallel. So in this proof, I know that angle 1 and angle 2 are congruent, and I'm trying to prove that the two segments, A and B, are parallel. We're going to use an indirect proof for this, even though in the past we've only used indirect proofs to prove that things are not true. But here's how this is going to work. So we're going to temporarily assume the opposite of what we're trying to prove. So we're going to temporarily assume that A is not parallel to B. So I'm going to adjust my picture so that A and B are not parallel. So I'm going to change my diagram. I'm going to draw B. Okay, I'm going to draw this transversal here. And then I'm going to draw A so that it's not parallel to B. And basically what we have now is angle 2 is still here, and angle 1 is now there. So basically, since A and B are not parallel, they have to intersect, as you can see. And when they intersect, the two segments along with the transversal form a triangle. Because we have a triangle, angle 2 is an exterior angle for that triangle, and angle 1 is a remote interior. So we know that angle 2 has to be greater than angle 1 by the exterior angle inequality theorem that we just proved. But this is a contradiction because the given says that angle 1 and angle 2 are congruent. So we came to a contradiction, therefore our assumption that A is not parallel to B is false. Thus, A is parallel to B. So think about what we started with here. We started with angle 1 congruent to angle 2. Angle 1 and angle 2 are alternate interior angles. So what we've just proven here is that if you are given a pair of congruent alternate interior angles, then the lines have to be parallel. And this is the theorem here. So if two lines cut by a transversal such that two alternate interior angles are congruent, then the lines are parallel. And the abbreviation that we will use for this in proofs is right here. Alternate interior angles congruent leads to parallel lines. Okay? So again, that was the use of an indirect proof because it's actually really difficult to prove that A and B are parallel directly. So we kind of went through the back door there by assuming that they weren't parallel and then showing that that was impossible. Now that we've proven this theorem, we can use this theorem to prove others. So here's another one. We're starting here with angle 1 and angle 2 congruent. Notice this time angle 1 and angle 2 are what we call corresponding angles. And we're going to try to prove that if corresponding angles are congruent, then the lines are parallel. Again, we're going to do this sort of informally. So we got angle 1 congruent to angle 2 because that's given. I'm going to throw an angle 3 in here. And we know that angle 1 is congruent to angle 3. because vertical angles are congruent. Therefore, angle 2 is congruent to angle 3. And that's by transitive. And what we're saying here is that if both angle 2 and angle 3 are congruent to angle 1, then angle 2 and angle 3 must be the same. Well, based on our previous proof, we just said that whenever you have alternate interior angles congruent, then you have parallel lines. And notice that 2 and 3 are alternate interior angles in this picture. So, new theorem. We started with corresponding angles, and now we ended up with parallel lines. So this is another theorem, and there's our abbreviation for it. So as I said, we have a lot of theorems to prove lines are parallel, but they're all pretty similar. It just depends on what angles we're given. So, here are the 6 ways to prove that lines are parallel. Number 1, we just proved in the previous slide. And that is slide number 6. Number 2, we proved in the very beginning when we first started the parallel line stuff. So that was slide number 5. Okay, so number 3 says that if alternate exterior angles are congruent, then we get parallel lines. So let's start with angle 1 congruent to angle 8. That's our given. Well, angle 1 and angle 8, so those are alternate exteriors. We're saying they are congruent. Well, we can say that angle 5 is congruent to angle 8. And that's because vertical angles are congruent. Therefore, angle 1 and angle 5 are congruent by transitive. And notice that angle 1 and angle 5 are corresponding. Therefore, we have parallel lines. Because the corresponding angles are congruent, we get parallel lines. So notice we used number 1 to prove number 3. And there's other ways too. I mean, we could have done so using number 2 to prove number 3. Okay, number 4 says, so we're given same side interiors are supplementary. So we'll say that angle 4 is supplementary to angle 6. We know that angle 6 is supplementary to angle 8. And that's just the definition of supplementary. So if 4 is supplementary to 6 and 8 is supplementary to 6, then that means that angle 4 and angle 8 must be congruent. And that is the congruent supplement theorem. Well, notice that angle 4 and angle 8 are corresponding angles. And when corresponding angles are congruent, lines are parallel. So again, we used number 1 to prove this. And similarly, we can do the same for same side exterior angles. So let's choose 1 and 7. So if angle 1 is supplementary to angle 7, we're going to try to prove that A has to be parallel to B. Well, 1 is supplementary to 7. We know that angle 5 is supplementary to 7. Definition of supplementary. if 1 and 5 are both supplementary to 7, then angle 1 is congruent to angle 5 by the congruent supplement theorem. And angle 1 and angle 5 happen to be corresponding angles. And we know that when corresponding angles are congruent, we get parallel lines. Okay, so the first 5 are all based on the 5 different types of angles that we have. Corresponding alternate interior, alternate exterior, same side interior, same side exterior. If any of those pairs, so if any of the first 3 pairs are congruent, or if any of the second 2 pairs, as in number 4 or 5, are supplementary, then we know that we have parallel lines. Now the last one is slightly different, and basically it says that if 2 lines are both perpendicular to the same line. Okay, so let's think about that. So here I have this line, right? We'll call it line C. If I draw A such that it's perpendicular to C, and I draw B such that it's perpendicular to C, then A and B have to be parallel. Algebraically speaking, we know that A has a negative reciprocal slope to C because they're perpendicular. Well, B has is perpendicular to C, so it also has the negative reciprocal slope. That means that A and B have the same slope, therefore they're parallel. So that's an algebraic proof. We can do the same geometrically as well. So what we can say, so in our given, we know that A is perpendicular to C, and that B is perpendicular to C. So angle 1 and angle 2 are right. That's by the definition of perpendicular. Therefore, angle 1 is congruent to angle 2, because all right angles are congruent. And since angle 1 and angle 2 are corresponding, A has to be parallel to B, because corresponding angles congruent leads to parallel. Okay, so how are we going to use this information to do a proof? Well, we're going to try to prove that we have a parallelogram. And notice that we have a little hint here. So basically we have to prove these 2 sets of lines to be parallel in order to have a parallelogram. So let's do this one formally. Well, I have AB congruent to CD, so let's mark that. Boom, boom. I also have AD congruent to BC. Boom, boom. We're going to next say that AC is congruent to AC. And that's reflexive. So now I have 2 congruent triangles by side, side, side. So triangle ADC triangle ADC is congruent to triangle CBA. SSS. So that means that angle 1 is congruent to angle 4, and angle 2 is congruent to angle 3 by CPCTC. Now it can sometimes be tricky when deciding which kind of angles you have and which lines are parallel because of those angles. So here's what we're going to do. We're going to take this angle 1 congruent to angle 4, and we're going to separately draw just the segments that make angles 1 and angle 4, and angles 1 and 4. So angle 1 is made by AD and AC. Right? There's good old angle 1 right in there. And angle 4 is made by AC and CB. There's angle 4. Now we have to ask ourselves, what kind of angles are angle 1 and angle 4? It may not be readily apparent to you because this picture doesn't look like things that we've studied before. But if we extend AD in this direction, and we extend BC in this direction, and we extend AC, now this should look more familiar. It looks like two lines and a transversal. The transversal being AC. That makes angle 1 and angle 4 alternate interior angles. And we know that if alternate interior angles are congruent, then lines are parallel. So angle 1 and angle 4 being congruent means that AD is parallel to BC. And that's alternate interior angles congruent leads to parallel. Well, we can do the same thing with angles 2 and 3. So I'm going to draw that in purple. So angle 2 is created by AB. So there's angle 2. And angle 3 is created by AC and CD. So there's angle 3. Notice angle 2 and angle 3 are also alternate interior angles. And because angle 2 and angle 3 are congruent, AB and CD are parallel. So because it's the same reason, alternate interior angles congruent leads to parallel, I can put that here in the same step. So now we've proven both pieces that we wanted to prove. And we're done.